Hey, welcome back to Math with Patrick. Today's October 23rd, and we're solving problem 296 from the Daily Epsilon calendar. And we should show why today's answer is 23, because that's today's date. So we need to find the largest prime divisor of the three-digit number that is 23 times the sum of its digits. Okay, I'm just going to try to hunt down this three-digit number first, and then I'll deal with this largest prime divisor part next. So it looks like we have a three-digit number. Let's just call it like, I don't know, ABC for the hundreds, tens, and then ones place. So we have a three-digit number ABC that is equal to 23 times the sum of its digits. So we could sum the digits like this, A plus B plus C. 23 times the digits could look like that. And then it's saying that the value of the number itself is equal to 23 times the sum of its digits. And I'm not going to just put ABC here, but I'm going to put the kind of expanded form where I do 100 times the hundreds digit plus 10 times the tens digit and then plus the ones digit. Okay. And maybe here we could try like expanding the left side. And then how about let's try to collect up some of our like terms. Given that we're working with digits today, so like A, B, and C can only be the numbers 0 through 9. The whole numbers 0 through 9. And none of them are negative, so I want to see if I can like collect these like terms in such a way where I don't have any negatives. So let's cancel out that 23A by subtracting it from both sides. That means we get a 77A on the right. And then maybe let's cancel this kind of 10B and the C by subtracting on both sides. Maybe you heard that. That's Quill. I'm going to go bring him over here. Alrighty, here he is. So let's subtract the 10B, subtract the C. We'll get 13B plus 22C on the left side. And then we'll get the 77A on the right. So it's a little bit hard here because we have three unknowns and only one equation that relates them, but I'm going to see if I can create multiple equations out of this one. So we know that B, C, and A, again, are all whole numbers. Also, I notice that like this over here is pretty easy to factor. This is just equal to 7 times 11 times A. And so this number over here is going to be composite, and it's going to have factors of 7, 11, and A. And so I'm going to think about this in terms of actually modular arithmetic right now. I know this like 13B plus 22C expression is going to be congruent to a few different things: mod, 7, 11, and then A. Essentially, the basis of like modular arithmetic is like cycling through the numbers. So like, let's say we're in mod 6 for a sec. We can count all the way up to 5. Here are our 6 total digits, hence the name like mod 6. But once we try to get to the number 6, we actually just cycle back down to the number 0. This way of thinking is really useful for solving these kind of problems that deal with factors and perhaps divisibility, especially when you're working with whole numbers. Also, everyone already knows an example of modular arithmetic, like clocks. Like 13 o'clock is the same thing as 1 o'clock mod 12, because after 12 things, we cycle back again. Anyways, 13B plus 22C should be congruent to, nope, not 7, but congruent to 0 mod 7. This is just another way of saying that it's a multiple of 7. I can also say that 13B plus 22C is congruent to, nope, not 11, 0 mod 11. This is the same thing as saying that it is a multiple of 11. And then it's also going to be congruent to 0 mod A. And I don't know what A is right now. It is a digit. Ideally, it's not 0, because then I wouldn't really have a three-digit number. If A were 1, then this would be obvious because every integer is a multiple of 1. But if A were anything else besides 1, then I would actually get some information out of this congruent statement. Now what I can do here is I can replace any number that I see with kind of those numbers that I can cycle down with. So in mod 11, 22 is the same thing as 11, and then 11 is the same thing as 0. So this 22 times c essentially is just the number 0 mod 11. So I don't really need to worry about it. 13b is congruent to 0 mod 11. And then the number 13 is the same thing as the number 2, again, cycling that down. And so now I get actually a lot of information about our digit b. 2b is congruent to 0 mod 11. And so that means, well, I was going to say one of two things, but it could mean a lot of things. Maybe 2b is equal to 0 itself. Maybe it's equal to 11 or 22 or 33. And then to solve for b here, we would just divide both sides by 2. So maybe b is actually equal to 0 or 5.5 or 11 or whatever 33 halves is, or 22. But knowing that b is a digit, 0 is the only possible value for b. So thinking about modular arithmetic has now helped me figure out that our middle digit, the tens digit, is 0. So let's see how that helps with our other equations. Well, knowing that b is 0, this term right here is 0. We can kind of cycle down this 22 by subtracting 7 from it. Or I guess we could subtract 21 from it as well, because that's just a multiple of 7. So this congruent statement is the same thing as just saying c is congruent to 0. Because again, like subtracting 21 from this would give us like 1c, and then this 13b is actually the number 0 because b itself is 0. So now we know that c is congruent to 0 mod 7, and so that again gives us some options. Maybe c is 0, maybe c is 7, and c is our ones digit, so I'm still not sure if we should pick 0 or 7 just yet. I guess we could double check and see what happens here. Because if we now kind of go back out of modular arithmetic, armed with the knowledge that b must be 0, and c could be either 0 or 7, now I'm noticing that if they're both 0, then a would have to be 0. And I guess that makes sense that the number 0, 0, 0 is equal to 23 times the sum of its digits. It just doesn't seem like a valid 3-digit number. So with that being said, it looks like c must be 7. Okay, cool. And then b is 0. So how about let's take a look-see at this equation, now knowing that c has to be 7. 22 times c is still equal to 77 times a. We could break up some factors and cancel them on both sides. And it looks like this 7 and that 7 cancel, this 11 and that 11 cancel, and so we're just left with 2 is equal to a. Cool. And so that completes our 3-digit number, 207. And we should see now what the largest prime divisor of this number is. Okay. So, well, it does say that 207, right, here's the 2 for A, the 0 for B, 7 for C, should be equal to 23 times the sum of its digits, 2 plus 0 plus 7. This is the number 9, so it looks like 23 times 9 is equal to 207. And the only prime factors that we're going to find out of that 9 are 3 and 3. So the largest prime divisor is this 23 right here. That is a prime number, and we aren't going to find any other prime numbers that are larger than that 23. So here's my solution, a little bit of modular arithmetic, a little bit of logic, I suppose, and finding that 207 is our lucky number and 23 is its largest prime divisor. So I think we're all done. Thanks for watching, and I'll see you tomorrow. Bye.